Dr. Becky Smethurst, welcome to the Astroben podcast. How are you?
I'm good, thank you, Ben. How are you?
I'm very good, thank you. I'm very good. Just chatting to you before we started recording. I've just got back from the International Astronautical
Mm.
Congress, which is very exciting for someone like myself who's kind of got one step in the industry, but I'm still feel very glad to be able to attend events like that. I understand you were traveling as well last week.
Yeah, I went to a conference called Dot Astronomy last week that was in New York City, which is all about astronomy online. So whether that's tools for research, like a lot of coding tools get built at the conference, sort of hacked on really, or whether it's education as well, whether that's teaching resources or science communication, to the public. It's all that sort of comes under that header of dot astronomy, and it's basically how can we do things better, better practices, and work better within the community. And it's such an inspiring conference every time I go.
Yeah, well, you're definitely a thought leader in that regard because you've got a very big social following. So
Mm.
when did you start this? When did you start? Well, first of all, let's start on your journey in astrophysics.
Yeah.
When did you start that, and where did your passion stem from?
I mean, I was just the kid who loved space, right? Who just asked endless questions. So I don't think I ever grew out of that. I think at school, I basically just, picked my favorite subjects every time, which eventually led me to physics and maths. And then I realized I could take astronomy at university. And it was at some point at university I realized actually we don't know all the answers. When I was a kid, you get all these space books with these big fact files, and it seems like we know everything. But actually, there's so much more that we don't know than we do know still. That's why we're still doing science. And the idea that, you could contribute to a little bit of human knowledge. You could add your little bit to the fact file of the space books was something that just really gripped me. And so that's what inspired me to get into research and do an astrophysics PhD. And it was while I was doing my PhD back sort of in 2013, 2014 at Oxford that I realized that communicating what I was doing back to the public was something that I A really enjoyed and B thought was really important. Taxpayers pay for a lot of the research that goes on at universities up and down the country, and so giving back in that way, but also to all the little kids that were as obsessed with space as I was as well, and the adults that have lost touch with sort of that aspects that they love as well, sort of engaging them with the cutting edge research that's going on was just something that I was like, yeah, this is something I want to do. And it was mainly, sort of like these like Astro on Tap events that you might have heard of that happen up and down the country where we do little talks in pubs, stuff like that. And then as I got out of my PhD, my first job was at the University of Nottingham, who have a really well-known YouTube channel called 60 Symbols. There's a physics YouTube channel. And while I was there, I got to make videos with them for that channel. And that was for about 2 years. And then I got a new job back at the University of Oxford. And they were like, well, you can't be on the channel anymore, but why don't you make your own? And I was like, yeah, sure. That sounds like something I could do in my copious spare time. And here we are. I've spent about 5 years basically making a video every single week on some aspect of astrophysics and astronomy. And it's led to two public science books as well. Space 10 Things You Should Know and A Brief History of Black Holes, which essentially is my way of communicating my absolute love and joy for all things black holes.
No, absolutely. And I guess it's kind of a smart career move as well because people who work in academia, and I wouldn't say notoriously, but that is definitely something that not all mathematicians and physicists and scientists have is an ability to communicate very complex ideas to simpletons like me. Um, so yeah, wait, and did you gravitate towards it like a duck to water? How did you feel when you first pressed record in front of the camera for the first time?
I think I gravitated towards explaining the science that I loved quite naturally because I think, with friends and family, as soon as you say, oh, I'm gonna go study astrophysics at university, they're like, what? Like, what even is that? What would you actually do all day? All that kind of stuff. And that really got me into sort of the groove of explaining things, in the way that like my mum, who is very intelligent but didn't necessarily have the education that I had, having left school at 16, like, could still understand kind of thing. And so making that transition from speaking to people in real life to sitting in your spare bedroom talking to a camera to yourself essentially was a bit of a weird leap because there isn't anybody there, and you do have to get good at pretending the camera is a person almost to so that it sounds natural. And I really do just picture my mum every single time when I'm talking. So maybe that's the key is to yeah, to do it naturally is to picture someone that you know and love.
No, it's brilliant, and to address the elephant in the room, we're obviously both from the United Kingdom,
Uh-huh.
and I don't think, well, the UK space industry is growing. We're probably one of the leaders in Europe, I would say, from a number of different disciplines. But science communication and space communication is quite US centric still.
Mm.
So did you feel like did you compare yourself to sort of American and sort of space influences, that
Not
sort of
really,
thing?
no,
You
because
just did your own thing.
I didn't really know that sphere at all. You know,
Mm,
the people that I was most aware of were Patrick Moore on the Sky at Night and Brian Cox on the BBC. They're both Brits. That was the space that I was more aware of, and I wasn't really aware of the social media sphere at all. Obviously, like NASA does have a big sort of presence in that sphere in terms of communicating a lot of results, but so does the Royal Astronomical Society, so does the
mm,
European Space Agency, and I think especially because my field is specifically astrophysics research with telescopes and not necessarily space exploration missions to anywhere in the solar system or anything that very much is, sort of NASA centric. I was maybe a little bit, sort of removed from that. And sometimes I do find people come up to me and are like, "Oh, did you see this latest rocket launch?" And I'm like, "That's not my thing. I don't care about sending stuff to space. I care about the stuff that's already in space that we can look at and figure out like what on earth is going on." So I think we do get conflated a lot of times, sort of the space exploration side of things and also the astronomy and astrophysics side of things. And there is a lot of overlap. Like, I think
mm.
space exploration is generally motivated by the need to do science, to say sending a probe to Mars or to Jupiter or Saturn or wherever you send it to. Um, and so we're sort of driving forward the need for that. In the same way that you drive forward technology, astronomy drove forward digital camera detectors, for example, and improvements in Wi-Fi and medical imaging and all this kind of stuff.
Mm.
But it's in that same sense, and so yeah, I never really sort of was aware of sort of the stuff going on in the States. So yeah, when I rocked up to the scene, people were probably like, "Who's this British lady just chatting
Yeah,
to me
she
about
just
black holes?"
she just won't stop talking about black holes. Well, let's touch on that because your book, A Brief
Mm.
History of Black Holes, which has been out about a year, but is now just being released as a paperback,
Hmm.
which I'll put the link on how to check that out in the show notes. But
Thanks.
perhaps you can tell us a bit about that book because subjects
Hmm.
like black holes. How can you make that brief? What's the where do
Yeah.
you start with something like that?
Well, this is the thing. It's just because there's so many misconceptions about black holes, which is why I wanted to write this book. And I think the way that you challenge those misconceptions is by taking people back to the beginning of our understanding of what they were and going through, okay, here's what we used to think, here's the data that was collected, and here's why we don't think that anymore, and why we think this instead. So challenging those misconceptions through sort of, literally like being holding the collective scientific hand of people doing all that research throughout the past century. And so challenge things like, people think that black holes are these endless hoovers, these endless vacuum cleaners just sucking up everything around them. But that couldn't be further from the truth either. People think of black holes as holes, but they're not holes. They're more like mountains of matter. And also they're not really black either. They're some of the brightest objects in the entire universe. Like, yes, the light can't escape from within what we call the event horizon, that so you have to be traveling faster than the speed of light to escape, but the material around black holes is accelerated to such huge speeds it starts to glow so that you can see it billions of light years away. So I mean, I said all of those misconceptions, and people are hopefully curious now as to see like why that's not the case and sort of learn more about them. And when you said, where do you start? I mean, you start with stars because stars are the only things that we know that make black holes. So we think, okay, how do stars fuel themselves? What happens when that fuel runs out? And therefore, how does the collapse occur? And so I went back essentially to our understanding of how we figured out how stars fuel themselves. We used to think that stars were fueled by coal and that the sun was burning coal the entire time, and through sort of the lots of research during the 1800s we figured out that wasn't the case, and lots of atomic physics and quantum physics and our understanding of hydrogen and atoms and molecules all had to come together for us to understand that stars were fueled by nuclear fusion. So it's things like that I think are so interesting, that I think even the sort of very keen astronomy nerds out there. Oh. Looks like my internet died. Where did you lose me?
You fell into a black hole. um, don't worry. I will. Let me start with another question. I'm sure it'll be fine.
Okay.
So I'm going to ask a really stupid question that sort of exposes my lack of knowledge about black
No
holes.
such thing.
All I know about black holes is what I've seen in Interstellar, which is
Which is
one thing.
not really, well, yeah, I guess one of them's a black hole, one of them's a wormhole, and everyone gets very confused.
No, exactly. And the other thing I remember is the concept of spaghettification, which is just a
My
thing that
favorite word
sticks.
ever.
Yeah, which I wouldn't be able to spell, but it sounds fascinating and terrifying. Is that is that still a theory that hypothetically, if you were to travel into a black hole, is that how it would happen? You get stretched out like spaghetti, or is that just the way of communicating the ideas to kids?
No, spaghettification is actually an observed phenomenon. It's not even theory. It's right. Sorry, let me do that again. So spaghettification is actually an observed phenomenon. It's not a hypothesis. It's accepted theory that this happens. So we've seen stars get too close to a black hole,
Mm.
and as the gravity's gotten stronger and stronger, it's stronger on one side of the star that's closer to the black hole than it is on the other. And so you end up stretching the star out. So, I mean, the technical term for that is tidal disruption event, but spaghettification is the process that we call that stretching. So, I mean, it's wonderful to think about, and I think it does evoke this sort of sense of wonder, this idea of spaghettification. And I do think that you should say that word as if you are Sean Connery every time you say it, because it just sounds so fantastic. But in terms of I think black holes in sci-fi is the way that a lot of people are first exposed to a black hole. And I think also it reinforces this idea in people's minds that they are physical holes in space, something that leads somewhere. Now, that's what we call a wormhole, and they're completely hypothetical. We've never observed anything like that. So, like you said, in Interstellar, they go through a wormhole next to Saturn, right? And they pop out somewhere else in the galaxy. Whereas a black hole is the exact opposite of a hole. It is a literal mountain of matter. And I go through this in the book as well. I cover this sort of this misconception that people have of black holes about where this idea comes from. And I think it's because when we think about gravity, and we explain it in terms of Einstein's theory of general relativity. We can think of it in the analogy we think of as like you've taken a bed sheet and stretched it out, or like a
Mm.
trampoline, and you've put something heavy in the middle of it. And that's what we like to think about as gravity curving space. And if you send you put a football ball. So if you put a football on the middle of a trampoline and then you send like a ping pong ball, like spiraling around it, that's almost like, the planets orbiting the sun or something. So you can imagine when you reach black hole that something's so heavy that you end up sort of compressing the trampoline so much that it's almost this steep-sided thing that nothing would be able to get back out of again. I think that's where we think of this idea of a hole and punching through space, but it doesn't go anywhere, a black hole.
Mm.
A lot of the questions that people ask me, sorry, let me say that again. One question that people ask me a lot is like, what's on the other side of a black hole? But it's like asking what's on the other side of the moon. It's just more space. If you go around the other side, a black hole doesn't lead anywhere. It is something that's very massive and dense, but it is still matter. We just don't know what that matter looks like because we can't get any information from a black hole because it's so dense that light can't escape.
Mm.
So I say in the book, they are literal mountains of matter. Is what they are.
So cool. Another thing from the book about the being beyond the event horizon, which again is a thing a lot of people kind of know the term from sci-fi, but don't really understand it. And you mentioned that the future is a direction in space rather than time.
Mm.
Can you help me mainly and our listeners grasp this concept and
Yeah,
what the implications are?
sure. So, I mean, the way we describe a black hole, so if we say this thing is a black hole, then what we're referring to is the space inside the event horizon. So we picture a sphere beyond which we don't get any light from. So if you were to see a black hole up close, it would look like this black sort of sphere in space. We don't know what's inside the sphere. Mathematically, you can describe it in terms of, okay, what does gravity say is happening in terms of maths, right? How strong is the gravity at each point in space? And so how we describe it is that all the matter, so say you had a star there beforehand, right, that's like 10 times heavier than the sun, right? And its core collapsed down into a black hole. Say the core was about 3 times heavier than the sun. Then all that matter ends up squished down into an infinitely small point. And you can't say how strong is the gravity there because essentially it's infinity. You've had to divide by 0 essentially. And so we call that point the singularity, right? So if you were going to describe a black hole, it's a sphere of the event horizon and then all the mass at the very center of that sphere. And so what it means is if you work out, okay, how strong is gravity in all the places beyond the event horizon? It's so strong that there's nothing that you can do to escape the pull of that gravity, right?
Mm.
So if you're the other side of the event horizon and you can travel at the speed of light, you can always escape at the last minute. You can get really close, nudge it, and then fly away. But once you're inside the event horizon, the only place you're going to end up is the singularity at the very center, with all of the stuff that makes you up adding to the mass of the black hole. So if you think about what that means is that, if you think about plotting out your future, where are you going to go in space in the future? Then the only place you're going to go is the singularity. So the future is no longer just something in time, it's also something in space as well, because you know exactly where you're going to end up in terms of your position in space in the future.
It's truly mind-boggling, and I'm sure you're kind of used to talking about these things for many hours a day for many years, but it's still so awe-inspiring. It's like the ultimate mystery, really.
I love sometimes just being sat at my desk doing research and you're so lost in the numbers of everything that you're doing, just crunching numbers, data analysis, making plots, that you don't always stop and think about it. And then occasionally I'll do a calculation where I'll be like, oh, okay, so the mass of this black hole at the center of this galaxy is a 3 million times heavier than the sun. And this one's 9 million times heavier than the sun. And then I'll just sit back and go, wow.
Yeah, it's
Just like
crazy.
take a minute to like pull myself out of that sort of data analysis hole and just appreciate like what I just did or what I just spent like a few hours doing. And I still get like a goosebumps and a sense of awe every
I'm
time I
sure
do
you
that.
do. Last week there was the Webb Space
Hmm.
Telescope, which is the gift that keeps on giving, and it's only
Oh
just
yeah,
started.
our
Um,
favorite new toy.
yeah, I read about how there's potentially hundreds of thousands of Milky Way sized galaxies that have been
Mm.
discovered way before we thought. Is that the correct interpretation? What was the main
I hadn't
discoveries
seen
last
that. What,
week?
way before we thought? What do you mean by that?
I think like around the billion year mark since the Big Bang, which
Do you mean
was
like spiral galaxies?
yes,
Oh, I
yes.
see what you're saying. Yeah.
Mm.
Okay, great.
What's the significance of that, and what discoveries has the James Webb Space Telescope made that are sort of redefining
Mm.
our our our, our understanding of the universe?
I think you've hit on the biggest one for me, especially in my field. So I study black holes, but I really study them, the supermassive ones that you find at the centers of galaxies. So to understand them, you've really got to understand how galaxies evolve as well and how they come to be. So with the James Webb Space Telescope, what you can do is because you can detect really faint light, you can see light that has been traveling for longer in the universe from like a bigger distance. And so that means that light that's, say, taken 13 billion years to get to us was emitted when the universe, like, it was emitted 13 billion years ago when the universe was less than a billion years old. And so you're seeing galaxies as they were when the universe was less than a billion years old, or less than 2 billion years old, or 3 billion, depending on how far back you look. And so what you can do with that data is sort of piece together how galaxies are evolving. Now, with the Hubble Space Telescope, it couldn't see that faint light, or at least not as far back. So we were sort of missing key sort of bits of the picture just working with the Hubble Space Telescope data. And also, Hubble is a much smaller telescope as well. It's only about 2 meters across as opposed to James Webb's 6 meters across. And so the amount of detail it could get at those distances, everything just ended up becoming a fuzzy blob. And so the farthest back that we've seen galaxies that have spiral shapes, like our Milky Way does, was around about 10 billion years ago. We were like, okay, so the universe is 13.7 billion years old. Then maybe after about 4 billion years is when spiral structure starts to form in galaxies. Because before that, we couldn't see it. Everything was just a fuzzy blob. But JWST has the resolving power to start pulling out, turning those fuzzy blobs and resolving them into the structure that they have. And it's starting to spot the spiral structure way, 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 way earlier than we ever thought it would exist. And so that's really key because of the way that we think galaxies form in the universe. When gas gets cold enough, it's very, very chaotic in the early universe. You probably have a lot of mergers going on of galaxies. And only when stuff has settled down enough, calmed down enough, do you start to get these beautiful, big spiral shaped galaxies. So our models previously had been like, well, we don't need that to happen until about 4 billion years. Whereas now we're like, oh, we might need that to happen after about a billion or so, which is a big change in how we think the universe has evolved, and
Mm.
also then has knock-on effects for like, okay, then how did the black holes at the center of them grow and get affected by the fact that you could have much calmer processes going on much earlier in the universe? Will it have slowed down the growth of black holes somehow? So it's a really big result, and it has a lot of knock-on effects as well, which I think are really, really interesting.
Massively. And with the advent of AI and AGI,
Mm.
which seems to be around the corner, for most people, it just involves playing around on ChatGPT, but certainly the application and integration into science and research is probably going to be the biggest
Mm.
leaps and bounds for humanity. Are you using AI or planning to, and how do
Hmm.
you think that's going to help increase your I guess
Yeah.
the speed of your results and
Hmm.
how far can it go?
It's so funny the sort of like mass hysteria, I guess you want to call it, over AI in the past year we've seen because I mean, I remember starting my PhD and people talking about using AI to classify galaxies, sort of image classification, things like that. And I think it's only because we now have almost like black box tools that are readily available rather than something you have to like code up yourself, for example. That I think it's become part of the mainstream. But I don't think what they can do has really physically changed that much in terms of what we use them for in academia already. So the way that I've used them before is to like classify images of galaxies. We have these big, what we call surveys in astronomy, where you have a telescope that instead of like, astronomers being able to be like, I want to use this to do my science, this little thing. Instead, like their job is to survey the entire sky, like split it up into little postage stamp shapes and just keep coming back night after night and taking little images of those same patches of sky and building up a big picture. And so you end up with a lot of images all with galaxies in them, all of different shapes, all that need classifying. And to be honest, AI isn't great at this. It's good at the easy ones, but the difficult ones you still need a human to do. And the way we've done this for a long time is a project called Galaxy Zoo. It's what's known as a citizen science project. So if you go to zooniverse.org or galaxyzoo.org, you'll find all of these different citizen science projects where scientists with too much data have essentially uploaded that data and asked, hey, the public, can you help us classify this science data? And so you can then use that as training sets for AI, obviously. And now we're in the stage where essentially we're going to have new surveys coming online, which are supposed to detect 1 billion galaxies in the universe, where we'll have AI running on it to classify the easy things and then leave the hard and interesting things for humans to do. Not necessarily hard, but yeah, more interesting, more complex structures, for example, which I think is a really interesting sort of use of like humans and machines working together almost, which has been great. But of course, we also love to play around with GPT-4, which, is the back end of ChatGPT. We like to write sort of like, can you write me an abstract for a paper that is about, this research or whatever, and see what it spits out, which is always fun, especially if you give it some very strange prompts.
Yeah, exactly. Well, it's definitely getting better by the month and year.
Language
really.
learning models are especially good, but I think it's not really those that are going to affect science and astronomy. It's definitely sort of the image processing.
But it sounds like
AI.
a big time saver, which is great. So it frees up your time to do to more important projects, I guess, like more macro thinking and.
Yeah, it just gets you the data you need quicker, I think, so that you can crack on and ask the big questions.
Well, speaking of the big questions, just the final thought before you go. I'm sure you've been asked this many a time, so sorry, and probably by kids. Do you think humanity will ever traverse a black hole?
Ooh,
Or come close, or do you think it will be, some sort of, autonomous vehicle? What am I trying to say?
oh,
A
okay, that's what I
satellite?
was going to say, was
Yeah.
define humanity. Because if I think we could send a probe, 100%. Do I ever think we'll send humans? No. I don't think anyone would sign up for that mission because A, it's a death sentence, and B, you can't communicate anything back from what beyond the point that we don't know anything from. Do you know what I mean? Like it would be very useful to send a probe to record the strength of gravity, like within the regions around a black hole. But like a human going beyond the event horizon would never be able to communicate anything back to us anyway. So personally, I mean, you'd also probably get spaghettified on the way. I wouldn't sign up for that at all. So no, I don't think like there will be any like missions planned to do so. I think it would be very likely if it turns out there's a black hole on the edge of the solar system, which is one hypothesis at the minute that I absolutely love. There's been this idea that this hypothetical planet 9, way out beyond the orbit of Pluto, that's around about 10 times the mass of Earth, just out there stirring stuff up on the edge of the solar system, but we've never found anything. And so a while back, someone was like, hey, what if it was a black hole? 10 times the mass of the Earth, it'd be about the size of a tennis ball. And so I think if that was the case, if we could prove that that was indeed a black hole, then I think that would be something that we would perhaps send like a Voyager style probe towards to investigate. And I think I would class that as humanity,
Yeah.
exploring a black hole.
Exactly. Well, it's certainly interesting to think about, and for someone who's not a subject matter expert, it's kind of exciting just to sort of look up at the stars and wonder about these big things. Just before you go, what do you do when you're not working? more sort of down to earth? Do you have any hobbies that you do to distract yourself from thinking about our existential
Oh, 100%.
place
Yeah.
in the universe?
So, I mean, I love to hike, so I do a lot of hiking holidays, and I also love to scuba dive. So I like to do it. I like to go to as many conferences on islands as possible, so I have chances to network while scuba diving is my, is my thing. But like when I'm at home, I mean, if I'm not working, I'm reading. Like I am devouring as much fantasy, usually fantasy over sci-fi, just because sci-fi sometimes I can't switch off my brain from being like overly critical of the science
Yeah.
like side of things. So usually I'm reading a lot of fantasy.
Fantastic. Dr. Becky Smethurst, thank you very much.
Thanks, Mim.